Hello, this is Richard Hammack's Calculus 1 course. Today is Lecture 6b, our second installment of inverse trig functions. Inverse trig functions Part B. Last time in Part A, we reviewed sine inverse and cosine inverse. Today we continue this investigation with the inverse tangent function, tan inverse, sometimes called arctangent, the inverse secant function, sometimes called arcsecant, and also the inverses of cotangent and cosecant. Now, of course, none of these functions is one-to-one, as you well know, so they don't technically have inverses, but just like with sine and cosine, we're going to restrict their domains so that we can take inverses, thereby coming up with some very useful so-called inverse trig functions. Let's begin by recalling sine inverse and cosine inverse. Remember that we define sine inverse of x to be the angle theta between negative pi over 2 and pi over 2, for which sine of theta equals x. This is the inverse of the sine function when you restrict its domain to these values of theta. It has a picture over here in this triangle that's on the unit circle with radian values between negative pi over 2 and pi over 2. This triangle has a vertical side x, so if you took sine of this angle right here, you would get x. So sine inverse of x is this angle. It's the angle that if you took sine of it, you would get x. Cosine inverse of x is the angle theta between 0 and pi, for which cosine of theta equals x. And here's its picture. We have radian measures between 0 and pi on the unit circle, and in our triangle shown here, the adjacent side is x, so cosine of this angle that's indicated would be x by definition of cosine. So this angle is the angle for which if you took cosine of it, you'd get x. So it is cosine inverse of x. And we worked out numerous examples last time and did some looked at some properties of sine inverse and cosine inverse. Today we're moving on. Let's begin by talking about the functions tangent and tangent inverse. I've drawn for you here a picture of the graph of tangent theta. Of course, this function is not one-to-one. A horizontal line will cross that function, that graph, infinitely many times. So we can't expect an inverse of the function tangent theta. However, if we modify tangent theta, if we restrict its domain only to include the values of theta between negative pi over 2 and pi over 2, in effect erasing the rest of the graph, suddenly we do have a one-to-one function. So this tangent theta with restricted domain is one-to-one, and it's going to have an inverse. Its inverse would be the running of tangent theta backwards from an output of x, tangent inverse of x. We'd get that by going over to the graph and down. We'd get to a theta here, a radian measure between negative pi over 2 and pi over 2, where if we took tangent of that, we'd get x. So literally, tangent inverse of x is the angle theta between negative pi over 2 and pi over 2, for which tangent theta equals x. That's our definition of tangent inverse. Again, it's not really the inverse of the function tangent theta because tangent theta has no inverse. This tangent inverse of x is the inverse of tangent theta with restricted domain, the inverse of the function indicated by this part of the graph of tangent. So I want to draw geometric pictures of this. And our pictures are going to come from the fact that if you take a right triangle whose adjacent side is 1, if you think about the length of the opposite side, let's see, opposite over adjacent would be tangent of theta, but here opposite over adjacent is just opposite. So the opposite side is equal to tangent of theta. So in this triangle right here, we have a geometric picture of tangent of theta. Draw a right triangle with adjacent side 1. The opposite side is going to be tangent of theta. And that's illustrated here in this picture with the unit circle. We've got our triangle with adjacent side 1, angle of theta. The opposite side is going to be tangent of theta. So as you can see here, if theta is really small, then tangent of theta is close to 0. As theta gets bigger and bigger and bigger, say closer and closer to pi over 2, 90 degrees, this opposite side gets bigger and bigger and bigger. It tends to infinity, which is exactly what's happening in the graph here. Let's draw a corresponding picture for tangent inverse of x. What it would be, or what it's going to be, is just this drawing for radian measures between negative pi over 2 and pi over 2, and with input and output reversed. Here input was theta, the output tangent theta was the side length of the triangle. We'll reverse that in this picture. So here is our triangle. The opposite side is x, which previously was the output here. And tangent inverse of x is the angle between negative pi over 2 and pi over 2 for which tangent of theta equals x. Well, this theta right here, tangent of that would be this opposite side x. So this angle is tangent inverse of x. So let's look at some examples of this, and I'll try to draw the picture of tangent inverse of x that we've illustrated here to underscore its usefulness. Let's look at tangent inverse of the square root of 3. By our previous definition, that's the angle theta between negative pi over 2 and pi over 2 for which tangent of theta equals the square root of 3. And we'll draw our picture over here. We've got our right triangle with adjacent side 1. And tangent of this angle would be square root of 3, so we're drawing that opposite side as square root of 3. Now if you look at this angle, this triangle, you may recognize that as a familiar triangle. It's double the size we normally see it, but this is the 60, 30, 90 triangle. Normally we'd see it that size, so it's inside of the unit circle. So it's a little bigger than normal. In the usual version of it, the horizontal side is 1/2, the vertical side is square root of 3 over 2. This is doubled here. So this looks like a 60-degree angle here. In other words, pi over 3 radians. So tangent inverse of square root of 3 is pi over 3. And we got that from looking at the picture. You'll also find yourself relying on your experience with working many problems for computing tangent of various values, and you will recognize from your experience that there are certain angles that you've taken tangent of that gave you square root of 3, and you may play around with it, or you may remember it, but play around with it for a second, and you'll remember, oh yeah, tangent of pi over 3, that's going to be square root of 3. And sure enough, double check that. That's sine pi over 3 over cosine pi over 3. That's square root of 3 over 2 divided by 1/2, and that simplifies to square root of 3. For another example, let's take tangent inverse of -1. So by our definition, that's the angle theta between negative pi over 2 and pi over 2, for which tangent of theta equals negative 1. And let's draw our picture. So we want to draw a picture where tangent of theta is equal to negative 1. So we'd be way down here, below the x-axis. So we're trying to draw a picture where you have an angle, and tangent of this angle would be negative 1. And sure enough, tangent of this angle would be negative 1, opposite over adjacent, negative 1 divided by 1, that's negative 1. So if we look at this triangle that we've drawn, its legs are equal. They're both 1. So this has to be a 45, 45, 90 triangle. And this angle here would be negative 45 degrees. That's negative pi over 4 radians. So we get negative pi over 4 as our value here. And if you've done a lot of these angles, even without drawing the picture, you'd remember that tangent of negative pi over 4 was equal to minus 1. So tangent inverse of minus 1 would be negative pi over 4. Let's talk about the graph of tangent inverse. So we're going to get the graph of tangent inverse by reflecting the graph of tangent across the line y equals x. But remember, we only use the portion of tangent that's between negative pi over 2 and pi over 2 to make it 1 to 1. So drawing the graph of y equals x, we now are going to reflect this graph of tangent across it, and we get this graph here in bold. That's the graph of tangent inverse of x. Now I'll do that again. Notice that these two vertical asymptotes in tangent, they're going to reflect over and become horizontal asymptotes in tangent inverse. Now allow me to erase everything else that we had before, that all of the graph of tangent and its asymptotes. And we just get the graph of y equals tangent inverse of x here. So notice as x gets bigger and bigger and bigger, tangent inverse of x gets larger too, but it stabilizes at pi over 2. As x gets bigger and bigger and bigger, tangent inverse of x is getting closer and closer to pi over 2. Let me remind you of why that's true geometrically. Here's our picture of tangent inverse of x. So x is the vertical side. This angle is tangent inverse of x. And notice that if x gets really small, this angle gets closer and closer to 0. And you see that happening here as x gets really small, closer and closer to 0. Tangent inverse of x also gets closer and closer to 0. But I want to concentrate on what happens as x gets big in this picture. As x gets bigger and bigger, tangent inverse of x gets larger too. And x could go all the way to infinity, straight up like this, and this angle would become steeper and steeper and steeper. It would open up, and it would be getting, this hypotenuse would be getting closer and closer and closer to a vertical line the bigger x gets. So this angle would be closer and closer and closer to pi over 2 as x gets bigger and bigger and bigger. And that's why you see the graph happening here, getting closer and closer to the line y equals pi over 2 as x goes to infinity. And similar remarks would hold for x approaching negative infinity. You just have this triangle reflected over the x-axis. So x would be down here. But you should think about the graphs of these inverse trig functions and compare them to familiar triangles as we've done here to convince yourself that all of this is in harmony. It's all consistent. Let's move on now to the functions secant and secant inverse. And I've drawn here a graph of y equals secant theta. And like any trig function, it's not one-to-one. It does not have an inverse. So we're going to restrict its domain to get an inverse. Now for restricting its domain, let's see, we could start at x equals, let's look at things that are positive. As x gets bigger here, this graph goes up. We wouldn't want to go below 0 because then you'd have a portion back over here and a horizontal line that would cross the graph. So we'd better use just this portion of the graph, and then down here we could use this portion of it. It's going to look kind of strange, but here is secant theta with a restricted domain to make it one-to-one. And pause and look at this graph and you'll realize that if you included any more of secant than what's indicated here, it would not be one-to-one. So this graph that's secant theta, for theta between 0 and pi, is a one-to-one function. So this function, whose graph is indicated in bold, has an inverse, and that's what we're going to be calling secant inverse. Secant inverse will work this way. It'll run secant in reverse, take an output value for secant, x, go over to the graph and down, and we arrive at an angle, a theta value between 0 and pi, for which if you took secant of that theta, you would get x. And this theta right there, that's what we're calling secant inverse of x. So in words, secant inverse of x is the angle theta between 0 and pi, for which secant of theta equals x. So secant of this theta equals x. And let's draw a picture of this. The picture for secant theta would look this way, at least if theta is an acute angle. We have, as we had on the previous page, the right triangle with adjacent side 1. And let's see, secant is hypotenuse over adjacent. So it's going to be the hypotenuse divided by adjacent, the hypotenuse divided by 1. So in other words, this hypotenuse is secant theta. So the geometric picture of secant theta looks like this: right triangle, adjacent side 1, hypotenuse is secant. And you can see here in this triangle, as theta gets bigger and bigger and bigger, secant theta, the hypotenuse, gets bigger and bigger too. And as x gets closer and closer to 90 degrees, pi over 4, secant of theta, this hypotenuse becomes vertical, approaching vertical, so it's getting bigger and bigger and bigger as the triangle gets taller and taller and taller. And you can see here, as x goes to pi over 2, as theta goes to pi over 2, secant of theta just goes to infinity. That just means this hypotenuse is getting bigger and bigger and bigger. Whereas as theta goes to 0, the hypotenuse of this triangle becomes shorter and shorter and shorter, but it's always just a little bit bigger than 1. And that's why secant of theta is bigger than 1 unless theta equals 0, in which case this hypotenuse coincides with this side length of 1. So here's our picture of secant theta. It's the hypotenuse of this triangle, as discussed here. And we're going to draw a corresponding picture for secant inverse. It's going to be this picture, but with theta between 0 and pi, so it'll be the upper part of the unit circle. And we'll run this picture in reverse. Here the input was the angle, the output was the hypotenuse. In the picture for secant inverse, the hypotenuse is going to be input x, and the output is going to be this angle, which will be secant inverse of x. So here's the picture. The geometric picture of secant inverse of x. So for any x, you want to know what is secant inverse of x? Draw this picture with a triangle with adjacent side 1, whose hypotenuse is x on the unit circle is situated here. And whatever this angle is, that's going to be secant inverse of x. It's the angle where if you took secant of it, you'd get this hypotenuse. That would be x. Unlike the function tangent inverse and our other inverse trig functions, you do have to exercise a little bit of caution with secant inverse, and the picture can be slightly misleading if you're not careful. What you have to watch out for is that, as I've drawn it here, I took x to be a positive number. And it could well be negative, and you'd be on this entirely different portion of the graph. So what I've indicated here with this triangle is really only for x positive, for x up here. Now, what if x is negative? The function will work this way. What is secant inverse of a negative value of x? Go over to the graph and then up here. And notice that you're going to get an angle between pi over 2 and pi as output. Whereas if x is positive, the output is between 0 and pi over 2. So what's going on there? Here's the way the picture is going to look. And this is the picture for x negative, where x is what you're plugging into secant inverse. For values of theta between 0 and pi, secant is going to be negative when x is between pi over 2 and pi, as you can see in this picture. So in our geometric picture of secant inverse of x is going to be bigger than pi over 2, but less than pi, as indicated here. And you can think of it this way. Secant is hypotenuse over adjacent on this side of the y-axis. The adjacent side is negative, so hypotenuse over adjacent would be negative, and you're down here in the negative secant realm. So for negative values of x, you put your triangle here, and secant inverse of x is going to be this angle between pi over 2 and pi. Now, if that looks a little bit confusing, we'll do an example of this just momentarily. And you of course, will work a lot of other examples yourself to get used to this. It requires a little bit of thought, perhaps, but not too much thought. Let's try secant inverse of 2. By definition, this is the angle theta between 0 and pi for which secant theta equals 2. And we're going to draw our picture. The input 2, x equals 2, is positive, so we know to put the triangle here on the right side of the unit circle. And the input 2 is our hypotenuse in our picture of secant. So we draw a triangle here with hypotenuse 2 and, of course, adjacent side 1. And secant inverse of 2 is going to be this corresponding angle. The angle where if you took secant of it, you'd get 2. What angle is that? Well, look at this triangle. You'll recognize that as a 60, 30, 90 triangle. Look, it's half of an equilateral triangle of side length 2. So that's going to be pi over 3. So secant inverse of 2 is pi over 3 from this picture. And if you're a less visual thinker and more of an algebraic thinker, probably you've worked enough secant problems, so you'll recognize what value you'd plug into secant to get 2, and you'll remember, oh yeah, I think secant pi over 3 gave me 2, and you check it. Secant of pi over 3 is 1 over cosine pi over 3, and that's 1 over 1/2, and that's 2. So we're good. Pi over 3 is the angle where if you took secant of it, you'd get 2. So secant inverse of pi over 2 is pi over 3. Let's try another one, secant inverse of minus square root of 2. Now here, the argument we're plugging into secant inverse is negative, so we're going to draw our picture with the triangle on the other side. So secant inverse of negative square root of 2, by definition, is the angle theta between 0 and pi, for which secant theta equals negative square root of 2. And here's our picture. So the hypotenuse is square root of 2. We interpret this as being on the left side of the unit circle because we're plugging in a negative here, negative square root of 2. So we draw our hypotenuse as square root of 2. The adjacent side, of course, is 1. Or perhaps negative 1 if you like, because it's an x-coordinate. And we want to ask, what triangle are we dealing with? Because that's going to tell us the value of this angle, which is going to be our secant inverse of minus square root of 2. Well, if you look at this triangle, after a second you'll realize, oh, that's just a right triangle. That's a 45, 45, 90 triangle. Because think about this missing side. By the Pythagorean theorem, it squared plus 1 squared has to be equal to square root of 2 squared. So this side length squared plus 1 squared equals 2. So this missing side here has to be 1. And you can see, aha, we're dealing with an isosceles triangle. It's a right triangle. Two side lengths are 1. So that's a 45, 45, 90 triangle with a hypotenuse square root of 2. So if this is 45 degrees right here, this angle indicated here would be 3 times 45, 135, or 3 pi over 4. So there we go. Secant inverse of negative square root of 2 is 3 pi over 4. And sometimes you'll have just so much experience with working out trig functions, you'll automatically recognize, aha, I've done this before. I've taken secant of 3 pi over 4. I believe I got negative square root of 2. Let me check. Secant of 3 pi over 4 is 1 over cosine 3 pi over 4. And that's 1 over negative root 2 over 2. And that's 2 over the square root of 2, negative 2 over square root of 2. And it doesn't quite look like negative square root of 2 yet, but if you rationalize the denominator, multiply this by 1 in the form of square root of 2 over square root of 2, you do get minus square root of 2. So double checking here, secant of 3 pi over 4 equals minus square root of 2. So 3 pi over 4 is the angle where if you took secant of it, you get negative square root of 2. So 3 pi over 4 is secant inverse of minus square root of 2. Let's talk about the graph of secant inverse. So secant inverse is this restricted secant function, or the inverse of this restricted secant function. And we're going to reflect that across the line y equals x to get the graph of secant inverse. So doing so, you'll notice that this vertical asymptote is going to reflect across and become a horizontal asymptote. And here we go. Drawn in bold here is the reflected graph secant inverse of x, with the horizontal asymptote at y equals pi over 2. And let me just erase everything else. So here is our graph of secant inverse of x. Now let's think about this for a moment. Let's first of all think about x being positive and see if this makes sense. If x is positive, to be on the graph you have to be bigger than x equals 1. And as x gets bigger and bigger from x equals 1, secant inverse of x gets closer and closer to pi over 2, 90 degrees. Let's see if that makes sense from our picture. X is the hypotenuse, and imagine you tried to make x small, like a smaller and smaller hypotenuse. Well, in this triangle, x would always be bigger than the adjacent side 1. So you can't have a triangle like this with adjacent side 1 and hypotenuse labeled x without x being equal to, without x being bigger than 1, or perhaps equal to 1 if the angle is 0. So that's why in this graph, you start out with the x values in the domain being bigger than 1, equal to 1 or bigger than 1. Because x is going to be a hypotenuse, and x is interpreted as a hypotenuse of this triangle. Now as x gets bigger and bigger and bigger, this hypotenuse gets bigger and bigger and bigger, this triangle. It makes the triangle get taller and taller. And as that happens, the secant inverse of x, this angle opens up and gets closer and closer to pi over 2. As the hypotenuse becomes closer and closer to being vertical, this angle gets closer and closer to pi over 2. And that's why as x goes to infinity, secant inverse of x is getting closer and closer to pi over 2. Whereas if x is negative over here, the situation looks this way. And as x gets bigger and bigger and bigger in the negative direction, this hypotenuse becomes more and more vertical, closer and closer to 90 degrees. So this angle, which is bigger than 90 degrees, gets closer and closer to 90 degrees. And you see that happening here as x goes to infinity. Secant inverse is just a little bit bigger than pi over 2, but as x gets bigger and bigger in the negative direction, it's getting closer. It gets smaller and smaller, but getting closer and closer to pi over 2. Whereas if x gets closer and closer to negative 1, this hypotenuse gets closer and closer to this value of negative 1 here. The hypotenuse becomes closer and closer to being horizontal, and so the secant inverse of x opens up to an angle of pi. You see that happening here as x gets closer and closer to -1, secant of x gets closer and closer to pi. So again, I'm saying all of this stuff to indicate that all of this is in harmony. The graphs, the definition of the functions, their geometric interpretation, it all fits together hand in glove. And it pays off to think about this stuff and read your text carefully and actively and think about it and sketch out some pictures to really become familiar with these functions. I'm going to say a few brief words about cotangent inverse. We haven't talked about that yet. We want this to be the inverse of cotangent. And here's the graph of cotangent theta indicated here. And of course, it's not 1-to-1, so we're going to restrict its domain for theta between 0 and pi. So we're just looking at this portion of the graph of cotangent of theta. This restricted graph is 1-to-1, so it has an inverse. If we run it in reverse, we take an x, go over to the graph, and come down to a theta value right here. So cotangent inverse of x is going to be this value of theta, where if you took cotangent of it, would give you x. Literally, cotangent inverse of x is the angle theta between 0 and pi, for which cotangent of theta equals x. Cotangent of theta equals x. And you can draw a picture of this, a geometric picture. I'm not going to do it here. We'll be kind of brief with cotangent for reasons I'll explain in a moment. And I'm going to compare this cotangent inverse to tangent inverse of theta. And you're going to see that there's a close relationship to them. So for that reason, I've got the graph of cotangent theta here and dotted the graph of y equals tangent theta here. And if you look at this, you could get the graph of cotangent of theta from the graph of theta by reflecting theta across the y-axis and then moving the graph over pi over 2 units. So think about that as we now draw the inverses of cotangent theta and tangent theta. We're going to take this line y equals x and reflect both of these graphs across, and we get a picture that looks like this. In bold, we have the reflected y equals cotangent inverse here. And also in dotted, we have the familiar tangent inverse of x from earlier in today's lecture. And if you compare the graphs of cotangent inverse of x and tangent inverse of x, notice that you can get cotangent inverse of x from tangent inverse of x by first reflecting tangent inverse of x across the x-axis, so it looks something like that, and then moving up pi over 2 units. So there's a relationship between cotangent inverse and tangent inverse. Cotangent inverse of x, as we've seen up here, is minus tangent inverse of x plus pi over 2. Reflecting tangent inverse across the x-axis and then adding pi over 2 brings the graph to coincide with cotangent inverse of x. Now for this reason, you'll find that in calculus, the function cotangent inverse of x, although it comes up from time to time, is not as common as the graph of tangent inverse of x. And one of the reasons is that you have this relationship. Anything you want to know about cotangent inverse, you can get it from tangent inverse. So maybe you should work a few examples of computing cotangent inverse of x for various x. It should be pretty clear how to do that. We'll be kind of brief here in lecture. Let's also talk about the function secant inverse of x. This is our last remaining trig function whose inverse we haven't discussed, cosecant inverse. So here's the graph of cosecant x here. And of course it's not one-to-one, so we're going to restrict its domain to just values of theta between negative pi over 2 and pi over 2. So it'll be this part of the graph here, as well as this part right there. So here's the graph of cosecant x with restricted domain, and that's a one-to-one function. So it has an inverse, and that inverse would work like this. To run cosecant x in reverse, take an output value x, go over to the graph, go down, you get a theta value, an angle, where if you took cosecant of it, you'd get x. And this point right here, this theta value, that's going to be cosecant inverse of x. So literally, cosecant inverse of x is defined to be the angle theta between negative pi over 2 and pi over 2, for which cosecant theta is x. And from that definition, you could work out lots of cosecant inverse of x values. But again, for this function, we're going to be kind of brief in lecture. We're going to look at the graph of cosecant inverse of x, and we'll get that by reflecting this graph across the line y equals x. But I want to compare it to the graph of secant inverse of x that we talked about earlier in lecture. So dotted, I've drawn the graph of y equals secant x with its restricted domain between theta between 0 and pi here. And we're going to look at the inverses of these two functions by reflecting both of them across the line y equals x. And in so doing, the situation looks like this. In bold, we have the graph of our latest inverse function, cosecant inverse of x. It comes in two-part here and also over here. And we're going to compare that to the graph of secant inverse of x, which is dotted. And notice that if you look at this for a second, you'll realize that you can get the graph of cosecant inverse of x from the graph of secant inverse of x by first reflecting the graph of secant inverse of x across the x-axis and then moving it up pi over 2 units. So this part reflects across to be something like that. This part reflects across to something like that. And then move that up pi over 2 units, and you get this. And the same for the other side. So the geometry of this picture can suggest that cosecant inverse of x is negative secant inverse of x plus pi over 2. And in fact, careful inspection reveals that to be true. So that's about it for today. In conclusion, we've undertaken a careful study of sine inverse, tangent inverse, and secant inverse. Sine inverse in the previous lecture. Today we're very careful about tangent inverse and secant inverse. Now it turns out that, as we discussed in last lecture, part A, cosine inverse of x is equal to minus sine inverse of x plus pi over 2. We have that identity. So in that sense, even though we made kind of a big deal about cosine inverse of x, you can always get it in terms of sine inverse. And also today we saw that cotangent inverse of x is negative tangent inverse of x plus pi over 2. And cosecant inverse of x is equal to negative secant inverse of x plus pi over 2. So the inverses of cosine, cotangent, and cosecant can all be understood in terms of the inverses of sine, tangent, and secant. And as you go on in calculus, you'll realize that because of that, the functions sine inverse, tangent inverse, and secant inverse sort of play a predominant role. So if you can work with those functions fluently, you're going to be in pretty good shape. And that's exactly why today we were kind of brief about cotangent inverse and cosecant inverse. You can get them in terms of tangent inverse and secant inverse. Okay, so that's it for today. You should work lots of examples and exercises. Think about this stuff. But when we move on, we're going on to part 2 on limits. We've now concluded our part 1 of the course, the function review. And starting next time, we can start on the idea that separates algebra and trig from calculus. And that idea is a limit. We use it to get at slopes of tangent lines. So I'll see you there. Goodbye.